Hello, and thank you for this opportunity. My team and I investigated the embedded problem from a distributed computational point of view. Our motivation was that we have countless computers on our hands in today's world. Tablets, phones, notebooks, and embedded systems like media players and intelligent household appliances lay around us. We could use their computational capacity for scientific purposes to, for example, boost the simulation of galaxies. The base concept is that there is a server with all the data, and this server sends out the data to clients as fast as they can process it. When the client finishes calculating an interaction, it sends back the result to the server. When all interactions are processed, the server updates the bodies and the next iteration can begin. For easy messaging between the nodes and the server, we used OpenMPI, an open message passing solution specially for high-performance systems. We've read about many algorithms, but in the end we chose the simple n-square algorithm as it is straightforward and easy to implement, so we could focus on distributed computing. However, any algorithm can be used which can be parallelized data independently. One great advantage of this method is that we can use vastly different nodes. When a node joins, the software enumerates its capabilities and uses the fastest possible implementation on that platform. This makes it sure that we use all the computing capacity available. For example, a node with a powerful GPU inside can use the GPU implementation as well, and another node with no GPU but a modern CPU can use the vectorized AVX solution. As this is our first time dealing with the embedded problem, we've learned a lot in the last month. We've learned the basics of distributed computing and its possibilities. Also, we've tried numerous implementations of different algorithms, for example the bars hub tree, and the fuzz tree generation using Morton keys. We've also learned a lot about problems of accuracy and consistency with the laws of physics. In this graph, we can see the time needed for a single iteration using the different implementations of the n-squared algorithm and the simple implementation of the bars hub tree algorithm. We've used an NVIDIA GTX 1080 for the GPU and an Intel i5 6600 for the CPU measurements. We've estimated the FPGA performance of Xilinx RTX 7 based on an ageless implementation of the algorithm. We can see that the FPGA with no float support does not perform well, while the GPU is clearly the winner with more than 2000 cores. It is also clear that the n-squared algorithm cannot compete with lower complexity algorithms like the bars hub tree. For the distributed system to work as intended, we need adequate bandwidth. On this graph, we can see the estimated bandwidth needed to calculate given interactions per second. Based on our GPU's performance, with a 10 gigabits per second link, we could connect around 65 of these GPUs to the server and use them at their full capacity. Thank you for your time and attention.